Okay, so we ended up here in class, so we're going to just finish out these notes really quickly. So we wrote out the Maclaurin series for sine, and we got that this was our general term or our infinite series right here. And remember, this series, if we were to graph both the sine of function and the polynomial function, the infinite polynomial function, they'd be exactly the same. And we're going to talk about where that is in a minute. So the next example said write a fourth degree polynomial. And what we mean by fourth degree is that the highest power on our polynomial can be the fourth degree, a power of 4. Okay, so if we think about sine of x, because we're only using a partial sum of the infinite series, we're now going to talk about, this is an actually approximation now. So if we look at the first forms, and sorry, let me back up with some notation. And I know in some classes we talked about this. Sorry, let's go back here. So if I get the Taylor series, so we use a T for Taylor, sometimes we can use a P for the polynomial, Taylor of fourth degree. So the 4 right there will tell us the degree of our Taylor polynomial. That means we can go up to the fourth degree but not over. So if we look back to our Taylor series or our Maclaurin series above this, we look at our first term. Our first term was x to the first power over 1 factorial. Okay. Our next term was x cubed. Let me erase that. Over 3 factorial. And if we go to the next one, that's going to be x to the 5th over 5 factorial. And I'm getting all of that from up here, from these terms right here. Okay, so that 5th degree would put us over a 4th degree. So that means we can't add that in there because it's going to be over the power that we want. So when we talk about the 4th degree, 4 is the highest it can go, but it's not necessarily going to be the highest in the actual series because of the fact that this, our 4th degree term, actually zeroed out. Okay, so this, even though it's to the 3rd power, this is still a 4th degree Taylor polynomial centered at x equals 0 for sine. And then we can use this to estimate what sine is. So our sine of 1, we can use our Taylor series to approximate, and plugging in a 1. Like in class I said, we like these polynomials because they're easy to calculate. It's just 4 basic operations: add, subtract, multiply, and divide. Those are our easier operations. So if we think about that 1 over 1 factorial, that's just 1 minus 1, and then 3 factorial is 6, so we get a total of 5 over 6, which is 0.8333. The actual value for sine, I believe it to be 0.9414. I think we checked in the calculator. So a little bit off. If we add another term to our Taylor, so let's say we went up to the 5th degree Taylor, we'd actually get a value closer to that 0.9414. So the more terms we go up, the more accurate our approximation is going to be. Okay, so when we talk about, so really the difference between the series and the polynomial is just the series, a finite set of the series. So a partial sum, we can think about it as a partial sum. So a Taylor polynomial has a finite number of terms, whereas the series has an infinite number of terms. So that's kind of the difference between them. So the polynomial will know what degree we're going to. The series, we go all the way to n approaches infinity, or n is infinity. Okay, so now let's talk about where this actually converges, because that's important. So we talked about all these convergence tests last week and the week before. So now it's really a time to start looking at and using them. So if we think about the series, and I'm just going to write out the general term for the series really quickly, or actually let's write out the series. So the series for sine, we said, was -1 to the nth power, so it is alternating, x to the 2n plus 1 over 2n plus 1 factorial. So if we think back to our series tests, and we think back to that pink sheet that we have that has all the tests on it. So there's 2 tests that we could really use. We can use the alternating series tests, which I believe in this case would fail. Okay, but because we have a mixed series, it really lends itself to using our ratio test. So when we talk about the convergence or divergence of a Maclaurin series, we're actually going to use the ratio tests in this process to do that. Okay, and this is where those tests start coming into play. So we're going to use the ratio test. And the ratio test first said to get our a sub n plus 1. So we're going to have this -1 to the n plus 1, and that's not going to matter in a minute. And then we get this 2n, or sorry, not 2, or x to the 2n plus 1 plus 1. So that gives me 2n plus 2 all over, same thing here, 2n plus 2 factorial. So remember, the ratio test was taking the limit as n approached infinity, and we looked at the absolute value of our actual a sub n. So that -1 to the n plus 1 is not going to matter because of the absolute value. So all I really care about is that x to the 2n plus 2. So I'm going to start splitting it up just like we often did. So I get that over, and then again with the factorial, 2n plus 2, that's our first one. When I subtract 1, I get 2n plus 1, and that's kind of what I want to see because that's my original denominator in my original series. And then we're going to divide it by the actual series, which in this case multiply by the reciprocal. And x to the 2n times x to the first. Okay, and in order for this to converge, the ratio test says this must be less than 1. So we're going to figure out when this series or when this limit is equal or less than 1. Okay, so now it's just about a bunch of algebra. So we're going to cancel out a whole bunch of things. So that cancels out that cancels out that, and we're left with the limit as n approaches infinity. We have an x squared on top and x on bottom, so x by itself, 2n plus 1 factorial. Oh, no, I'm sorry, I canceled out the wrong one. This should be, we should have canceled out that one right there. So 2n plus 2. And this must be less than 1. Okay, let's undo that really quickly. Okay, I meant to cross out that one there. Okay, and this must be less than 1. But if we think about our limit is as n approaches infinity. So this has an x and an n in it. For the limit purposes, our x is actually a coefficient. So we're going to treat it like that. And most of our coefficients we moved inside and outside the process. We're going to do the same thing here. We're going to go the absolute value of x. We're going to bring that up. The limit as n approach infinity of 1 over 2n plus 2. Okay, and we're seeing if this is less than 1. Now, if we think about the limit as n approaches infinity, our numerator is growing slower, it's just 1, than our denominator. So our denominator is growing fast, which means our limit is going to be equal to 0. And then 0 times the absolute value of x gives us 0, and 0 is less than 1. When you get a true statement here in this process, because it won't always be true, when you get a true statement, that means that the series will converge for all x values, which is kind of nice because that means everywhere on our sine function, no matter what our x value is, this series is going to be the exact series, which means we can get a good approximation for any value of x that we want by using our polynomial series. Okay, so kind of the guideline to creating a Taylor series is simply the first thing we want to do is to, in fact, differentiate, find a lot of derivatives. Okay, then we're going to use the formula where our nth derivative and n factorial match. And remember, we're going to stick this in front. This is a coefficient of x to the 0 or the center to the nth power. So that's going to match too. And then really all we're doing is plugging in to that formula and then figuring out the general form. Okay. So the last example says, write the first four terms of the Maclaurin series for f of x equals sine of x squared, including the general term. I'm going to stop right there, and we're going to start there on Tuesday. Or on Wednesday, sorry. So what I want you guys to do is to look at the practice that comes behind the sheet that you guys got today in class, and I want you to go through the front, go through the back. Find the Taylor series for e to the x and the Taylor series for cosine of x, because those are the two that are important in addition to the sine function that we did in class. So if you have any questions, email me, come see me on Wednesday morning.